In 2020, there was a breakthrough result involving the halting problem and quantum entanglement. This video explains what it was. Decision problems are problems that have a yes or no answer. Is n a prime? Is string s a palindrome? Is Boolean formula f satisfiable? Does program P halt? Let's focus on the primes problem. We'd like to build a computing machine that solves it. For every valid input, it should think for a while, then output the correct yes or no answer. We can characterize a decision problem by the set of strings for which the correct answer is yes. In this case, it's the infinite set of strings that represent a prime number. Such a set is called a language. For the palindromes problem, the language is the set of all strings that are palindromes over some alphabet that we chose. So generally, we can define any decision problem using a language. Given some arbitrary language L, we'd like to build a computing machine that solves the corresponding decision problem. It's also common to say this machine decides the language L. When given an input that is a member of L, the machine should say yes. When given an input that is not a member, it should say no. Another example we'll discuss is the satisfiability problem. It involves Boolean formulas, so let's briefly describe them. A formula contains Boolean variables. This example has the variables a and b. They are connected with the logical operators and, or, and not. This formula reads a or b and not a. To evaluate its truth value, we need to choose an assignment and substitute each variable with the value assigned to it. Now we'll evaluate each operator. True or false is true. Not true is false. True and false is false. So for this assignment, the formula is false. Let's try a different assignment. We got a true result this time. This means this formula is satisfiable. It has an assignment for which the result is true. Here's one that is not satisfiable, also called a contradiction. A and not A. Trying both assignment options will prove that. And this one is a contradiction too, though it's a bit more subtle. It results with false for all assignments, but let's just demonstrate one. SAT is a language containing all the satisfiable formulas. So the decision problem is to tell whether a given formula is satisfiable or not. Some languages are more complicated than others. We classify their complexity based on how much resources their computing machines consume. One such class is polynomial time. This means we need to commit to some polynomial, for example, n squared, limiting how long the machine is allowed to run. If we feed this machine an input of length 5, its runtime cannot exceed 25 time units. And if we feed it an input of length 10, then it must finish within 100 time units. A machine that satisfies the polynomial time constraint is considered to be efficient and practical. For example, this palindrome solver is very simple, so its runtime is bounded by a linear polynomial. It is common to specify only the degree of the polynomial and omit the specific coefficients. The prime solver's runtime is not worse than a degree 7 polynomial. N here is the number of digits in the input. A deterministic polynomial time algorithm for this problem was only discovered in 2002. Another class is exponential time. Here, we bound the runtime by 2 to the power of some polynomial. This is no longer considered efficient, since even for relatively small values of n, the runtime can be millions of years. Now let's draw a diagram. The polynomial time class is called P for short. It contains the palindromes, primes, and many more interesting problems. The exponential time class is called exp, and it is much bigger. It contains the satisfiability problem. SAT is believed to be outside of P, though this was not proven. Here's how a simple SAT solver works. Given a formula, it tries all possible assignments. If it finds one for which the result is true, it says yes. And if all possible assignments result with false, it says no. Here it had to test all 8 possible assignments. Generally, the number of possible assignments is 2 to the power of the number of variables, and therefore exponential. For 50 variables, this machine would need over 10 million years. But note its low memory consumption. It allocates a small amount of memory for the first trial, and then reuses it over and over again. So while it's not time efficient, it is memory efficient. Its space usage can be bounded by a polynomial. The class of all decision problems that can be solved in polynomial space is called PSPACE. PSPACE contains P and is contained within exp. See a link in the description for a short video proving that. Now let's continue to the class R. Here we have no constraints over our machines. They can use as much time and as much memory as they want. We just require that they will eventually halt and produce the correct answer. All the decision problems that can be solved are here, and they're sometimes called decidable or computable. The most famous problem outside of R is the halting problem. We'll define it here as follows: the set of all Python scripts that halt. That is, the decision problem is to detect whether a given Python script halts or not. We'll see examples in a moment. Alan Turing proved in 1936 that such a problem is not computable, therefore it has no solver, and is outside of R. See a link in the description for a video visualizing this proof. The halting problem is in a class called RE. Here we relax our requirements even further. We require the machine to produce an answer only when the answer is yes. When it should be no, the machine is allowed to go on running forever. Since it's not always producing an answer, we'll call it a semi-solver. Here's how this semi-solver handles the halting problem. We'll feed it with a Python script that contains a 10-iteration loop. The machine will simply run the program, and if it halts, it will say yes. Now we'll feed it a script that contains an infinite loop. The machine will run this script forever and get stuck. Let's get back to the SAT problem. This machine is not a SAT solver, but a SAT verifier. Instead of searching for a satisfying assignment, it expects to be given one as proof for satisfiability. All it has left to do is just to verify this assignment satisfies the formula. If it does, the verifier outputs accept, which means it was convinced by this proof. Otherwise, it outputs reject, which means it remained unconvinced. This task is easily achieved in polynomial time. Now here's some arbitrary language L. We'll define what verification is in the form of a game with 2 players. The verifier, an ordinary machine constrained to run in polynomial time, and a prover, a magical, all-powerful machine. It can instantly solve difficult problems, but it has one small flaw. It sometimes turns malicious and lies. The prover's goal is to prove that the input is a member of L. It should send a proof to the verifier, and the verifier should check it within polynomial time, and decide if this proof is accepted or not. We have 2 requirements from the verifier. The first is called completeness. If the input is a member of L and the prover is honest, the verifier must accept. The second requirement is called soundness. If the input is not a member of L, the verifier must reject no matter what. An honest prover will simply admit there's no proof, and the verifier will reject immediately. But a malicious prover will provide a false proof. The verifier must detect this is a lie and reject. As we saw before, building a SAT verifier is easy. The prover instantly knows this formula is satisfiable, and it can prove it with a satisfying assignment. The verifier will make sure it is correct. If we input a contradiction, a malicious prover might try to cheat, but the verifier will see it as a lie. The class of all languages that can be verified in polynomial time is called NP. NP is believed to be larger than P, but whether this is really so is a famous open question in computer science. We'll now prove a more modest claim, that NP is contained within PSPACE. Let L be some language in NP. Therefore, it has a polynomial time verifier, and it satisfies our completeness and soundness requirements. Let's assume the polynomial bounding its runtime is n squared again. So if we feed it with an input of size 5, the proof sent by the prover can't be longer than 25 letters. Otherwise, the verifier won't even have enough time to read it, let alone verify it. Now we can simulate this game inside an ordinary machine, creating an L solver. Of course, we can't simulate a magical machine, but we can scan every possible string up to length 25 and check if the verifier accepts it. If we find one it accepts, then the word is surely a member of L. And if it rejects all of them, the word is surely not a member of L. So this is a correct L solver, and it runs in polynomial space, QED. And here's another language, unsat. It is the complement of sat, the set of all contradictions, formulas that are not satisfiable. It is believed to be outside of NP. Let's see why. The solvers of sat and unsat are identical, except their answers are flipped. But the verification game is completely different. The prover's goal is to prove that the input is a member of the language, but now this means it needs to prove a formula is not satisfiable, and the proof should be verifiable in polynomial time. It is believed there's no such proof. Let's also try to build an efficient halting problem verifier and see where we fail. It's easy to see this program halts, but let's pretend this is a difficult example. The prover instantly sees it halts, and it can even tell us when. To verify it, the verifier will have to actually run it the specified amount of time. But this can't be done in polynomial time. Even short programs can take an arbitrary long time to run. This we know for a fact. The halting problem is provably outside of R, far, far away from NP, the class of languages we can efficiently verify. So it looks like verifying the halting problem is way beyond our reach. But is there something we can do to get more verification power? We can of course allow the verifier to run in exponential time. This class is called nexp, and it is believed to be bigger than exp. This verifier can verify proofs that are exponential in size, but it can take millions of years, so it's not practical. And here's a verifier that has no constraints except that it must halt. It can handle proofs of any finite size, and it's easy to show such verifiers cover all of RE. But again, it's not practical. So the challenge is to keep the verifier efficient, but still be able to verify a larger class of problems. Next, we'll show some surprising ideas how to do that. Our first enhanced game is called IP, Interactive Proofs. Here, the verifier can interrogate the prover with a series of questions and answers instead of just one, and it verifies each answer that it receives. We have the same completeness and soundness requirements, except the verifier is now probabilistic, and it satisfies them not always, but with high probability, say 99%. So here are the updated requirements. If W is in L and the prover is honest, then with high probability the verifier will accept. If W is not in L, then with high probability the verifier will detect one of these answers is a lie. IP increases our verification power to cover all of PSPACE, including unsat. The unsat verifier is complicated, so here's a simpler example. Two graphs are said to be isomorphic, if by reordering the nodes we can make them identical. These two graphs are not isomorphic. It's easy to prove that graphs are isomorphic. The prover should only specify how to reorder one of the graphs. The verifier should reorder it as specified and check if they are now identical. But similarly to unsat, proving that two graphs are not isomorphic is more difficult. Using interactive proofs, it is quite simple. The prover always gets to first see the input. Then the Q&A starts. The verifier randomly selects one of the graphs and sends it to the prover, randomly shuffled. The prover should reply which graph it is. Since the two graphs are not isomorphic, the prover can easily distinguish between them. We repeat this several times. here the verifier always accepts. If the input is two isomorphic graphs, the prover has no way of knowing which of the two was sent. After being shuffled, they are indistinguishable. If it wants to fool the verifier, it has to guess. It has some chance of guessing right, but with a few repeated trials, its luck will eventually run out. But there is some probability that the prover will be lucky and the verifier will accept. With 7 questions, we can reduce the probability of this occurring to below 1% as we required. The next game is called MIP. It has multiple provers. If the provers are honest, it makes no difference. A single all-powerful machine can provide all the information we need. It's when they are malicious that things become interesting. Before the game begins, the provers are allowed to talk and plan how they're going to fool the verifier. But once the game begins, they're no longer allowed to communicate. The provers are all powerful, except they're not telepathic. Each has no idea what question the other one received. So this is like interrogating 2 suspects in separate rooms. If they lie, they might contradict each other and get caught. This significantly increases the power of the verifier. We can now efficiently verify every language in NXP. Our final game is called MIP star. Here we equip the provers with entangled particles. Quantum entanglement cannot be used for communication, but it can be used for subtle coordination between the provers. The top prover measures a particle and obtains some 0 or 1 result. Because of the entanglement, this has an immediate effect on a particle of the other prover and will influence its measurement result. This allows the provers to coordinate their answers in ways that are impossible with classical physics. For a video showing a concrete example of this in action, see a link in the description. It also explains why this doesn't count as communication. Since we gave the prover some new power, we expect the verifier's power will shrink a bit. But then it turned out the verifier has strategies that nullify this new toy, and MIP star is at least as big as MIP. Then it turned out the verifier can turn the tables in this game. By playing the provers one against the other, it can exploit the entanglement for its own benefit, making MIP star even bigger. In 2020, the full size of MIP star was discovered. It is equal to RE. Here's an efficient halting problem verifier. Given a program that halts, the provers can quickly convince the verifier of this fact. The success rate is 100%. That is, even though we tolerate errors, the verifier will always accept in this case. But in order to work properly, the provers must have a sufficient number of particles, or dimensions of entanglement, say 50 for this input. If they had less, they would have failed. Now, a program that doesn't halt. The verifier is likely to reject, even if we give the provers 1,000,000 dimensions. Here there might be errors, and the verifier might accept. The probability of this occurring is below 1%, as we required. Note, however, we can only verify the halting problem, not solve it, not even with quantum computers. But here's a thought. Let's try this game on some program W. We don't yet know if it halts or not. Can we simulate this game inside an ordinary machine? We can't simulate the magical machines. But as we did before, perhaps we can search through all their possible strategies. If we find one that the verifier is likely to accept, then W halts. Otherwise, it doesn't. Here, we also need to search through all the possible ways they can use the entangled particles. For this, we need to specify how many dimensions of entanglement the provers have. Say they have 10. We can compute that the best the provers can do is have the verifier accept with probability of 0.3%. But now we can repeat this computation with more dimensions. With a sufficient number of dimensions, the provers succeed in convincing the verifier. This means that W halts. Now let's try a different program, V. the probability remained low. It's either because V doesn't halt or because we didn't run this search long enough. So we'll never be sure that V doesn't halt since we can always try more dimensions. Therefore, this is not a solver. This is an RE semi-solver. If the answer should be no, it keeps running forever. But we can do more. This search models the entanglement using a finite dimensional tensor product model. It gives us the best probability the provers can achieve with finite dimensions. There is a more general model called the commuting operator model, which allows infinite dimensional entanglement. If the provers share infinite dimensional entanglement, then there is some specific probability that they can achieve. We have a search algorithm that computes this value by computing an upper bound and gradually improving it. If we continue searching, this upper bound will converge to the correct value. And now a question. Will the two search algorithms eventually converge to the same value? We can phrase this question differently. If we have a tensor product with many dimensions, is it approximately as powerful as an infinite commuting operator model? Consider this analogy from geometry. This polygon has a finite number of sides, and its area is smaller than the circle's area. But as we add more sides, we can approximate the circle's area as closely as we want. So basically, we are asking if the same thing happens here. This is an informal statement of Tsearelson's problem, which was an open question in mathematical physics for several years. Surprisingly, we are about to use complexity theory to solve it. Let's assume that the answer is yes. The left search converges to the best value that can be achieved with finite dimensions. The right search converges to the best that can be achieved with the infinite model. Our assumption says it's the same value, so the two search algorithms will eventually get very close to each other. But this can be our cue to stop searching. So let's combine the two searches in a single machine. It performs both of them in parallel. When fed with a program that halts, the lower bound will eventually rise to 100%, as we saw before. And if the input program doesn't halt, the lower bound will always remain below 1% because of the soundness requirement our verifier satisfies. So at some point, the upper bound will converge to a low value as well, and we'll know we can stop. This is a full-fledged halting problem solver. But it's a mathematical fact that there is no halting problem solver. So the assumption that brought us here is wrong. The answer is no. Infinite dimensional entanglement can't be approximated by the finite tensor product model, and is way more powerful than any finite dimensional entanglement. For some input program V that doesn't halt, with finite dimensions the provers cannot pass the 1% limit. But with infinite dimensions, the provers have 100% success rate in fooling the verifier. Because even a slight decrease would cue us that V really doesn't halt, and math forbids us from getting this cue. So we can efficiently verify every language in RE. We can efficiently verify arbitrarily long proofs. But are there any interesting languages outside of RE? Of course there are. Not halt, the complement of halt. Proving that a program doesn't halt is even harder than proving that it does halt, and it cannot be done with a finite proof.